So hi everybody, my chemistry kids. Just wanted to record a little bit of what I taught Thursday, and on these slides and on the copy that you have, it's pretty much filling in the information about energy and what it is generally and then how it applies to chemistry, and that's what this first page is about. You can read all this in the beginning of chapter 15 um, in the book. And as you go through these pages, these slides, it talks a lot about kinetic energy and potential energy, just like the terms that you learned in earlier science classes. But what we are covering is kinetic energy, as you look up here, is as it's proportional to temperature. Like how much motion molecules have is a reflection of its kinetic energy, and that is directly measured by the temperature the, um, the particles, and that temperature is directly proportional to the kinetic energy of the particles. So I wrote this little equation over here on the left, and it just means that with decreased temp, kinetic energy goes down. With increased temperature, there's more kinetic energy, and this is what is of the particles. It could be like the kinetic energy of anything in motion, but we're now getting down into the particles itself. Now the potential energy is going to be with um, the actual energy in the chemical bonds of the molecules between the atoms. And so we're going to get more into that with chemical reactions later in the year. But right now we're trying to apply these two terms, kinetic and potential, as it pertains to the chemicals themselves. Okay, and it all goes in with all kinds of energy is transformed into different forms, and that transformation is the basis of the law of conservation of energy, or the first law of thermodynamics. As we go into the next page, we want to talk about the three areas of how we're going to work in heat, and that's with chemical reactions, through changes in state of a substance, and through the exchange of heat between materials. Now, we talked about that in terms of temperature changes, okay? But we now are going to be doing it with phase changes, okay? So that's what this bottom little additional stuff is about. Also, I pointed out the differences between heat and temperature, and later next week I will have us actually get into this and draw pictures and diagrams. But the main gist about heat is it is very closely related to temperature, but it also is this energy flow, this transferring from warm to cold. This is the main emphasis for heat and how it is directly in with temperature. Now, the other thing about it, and I know I didn't point this out to the class on Wednesday, is that heat is uh, a derived unit. Let me get rid of that air. Heat is a derived unit, and temperature is a base unit. Okay, so we want to make sure that we get that okay, heat is derived, means you have to calculate it and do a lot of math calculations, the kind of derived unit we talked about earlier in the year, and um, temperature is a base unit. You can just get directly with a thermometer. Okay, so just to point out that temperature is a base unit, heat is a derived unit. You have to do calculations with heat, but temperature is directly measured with a thermometer. Okay, also guys, I didn't need to go over any of the heat units again. We did that earlier in the unit, but I wanted to point that out. That's where they would have gone in if I would have been teaching that for the very first time. Okay, as we go on to the second side of your notes, this is going into how we bring in the words system and surroundings, and that heat that we're talking about is that transfer, so we have to label the item that we're studying, which is system, and that item that we are looking around and the outer parts of its surroundings. So the item that we're studying is system, and everything else around it is the surroundings. So if we put it into simple phase changes, it's like if we went from gas to liquid to solid, that system would be giving off energy, having a negative joules, and becoming exothermic. Well, if you went from a solid liquid to a gas, that would be the system is gaining the heat. Okay, and there's examples there like cooling water, heating up water, that kind of thing there in the notes. Again, I'm trying to reemphasize that we do follow the law of conservation of mass even in phase changes as well as temperature changes. Okay, the other part that I covered was about how we have the basic Q letter for heat, but there's a lot of applications with heat when we're not at constant pressure, like the constant pressure with gases or constant pressure of the atmosphere. And when we're not at those constant pressures, then we have a lot more integrated math, but we're just going to be basing everything at a constant air pressure. And so we're going to call that another official name called enthalpy. Now, you'll see a delta H equaling the word enthalpy, and you'll see that a lot in your future college courses, not necessarily much more with me. Other than that, it's used for this heat constant that we're going to use for this second equation for our second half of our math for this unit. And it's going to involve Q, the Q that we've been talking about, equaling a heat constant of the phase change times the mass. And this is a list of all these constants on the next page, which you have a copy of. And it is these values of joules per gram. And I've got this listing of 5 chemicals: water, ethanol, methanol, acetic acid, and ammonia. Each one of them have a different amount of joules per gram. And you notice that with boilings here and condensings here, liquid to gas and gas to liquid, the numbers are the same, but when you do boiling, you have to give in the heat. Condensing, you give off the heat. So one set of numbers are positive and one set of numbers are negative. The same goes with melting and freezing. You have a set of numbers that are positive for melting and negative for freezing. And you're going to use these numbers like the C constants were for the previous temperature change problems, but you're going to be using these numbers for your current homework that you're doing on phase changes. How much energy does it take to boil? How much energy does it take to melt of water or of ethanol? It's this many joules per gram, this many joules per gram. And kind of note that it takes a lot more heat to boil and condense than it does to melt or freeze. So when you look at this set of constants, I kind of separated into these 4 lines on your note sheet. We got them for melting, we have it for freezing, we have it for condensing, we have it for boiling, and each one has this delta H, or the enthalpy of melting or fusion, the enthalpy of solidification, the enthalpy of condensation, the enthalpy of vaporization, okay? And each one involves the phase changes, okay? Now going from gas to liquid and liquid to solid, these are going to be negative, exothermic. When you go from um, solid to liquid or liquid to gas, it's going to be endothermic. Okay, so here are some problems that you're going to be seeing on the homework. And you're going to always use the delta H of the constant times the mass equaling the heat. So I have the first example, I had a couple mistakes on my wording, but it's basically solid acetic acid being melted if you have this many joules that are available. Okay, so I have it set up down here on my slide. Another one is this: so much ice being melted. How many joules are needed to melt so many grams of ice? So I'm going to go over to the board here. Hopefully you can hear me in the mic as I move it across the room. Okay. But here I have the first problem is 3455 joules, and we're going to put that on the Q, and that's going to equal the delta H that we have to get off the list times the mass. This is what we don't know is the mass, but we have to look up the delta H, and it's going to be of acetic acid. So we have to going to use the one for water, which is 333 joules per gram. We're going to use that number as well. So let's go ahead and copy them both down for the two problems. And so for acetic acid, we are going to use the 195. It is the joule per gram for every 1 gram, 195 joules. Almost could use these as conversion factors. You can flip them one way or the other, but we're going to stick to the equation for this unit. But you could look at it like a conversion factor like we did in Chapter 2. But when you do this, you're going to have 355 on the left, the 195 on the right, and you got to get rid of, get rid of the numbers so you have m by itself. So you're going to take 334.55 and divide it by the 195, and that's going to get the numbers all together, and so that's going to equal your mass. When you do the mass is going to equal 17.7, and there's even one more number, I think, that goes with it, one more digit, but basically the answer is going to be 17.7 grams of acetic acid. And then if we did the water example, we're going to have how many joules are needed, and it's going to be equaling the constant for water, which is 333 joules per gram. And we're just going to take that and multiply it by the 255 grams. And when we do that, we're just going to take 255 and times that by the 333. 255 times it by the 333, and we're going to get 84,915. Now you don't need all those significant digits, but when you look at that, you're going to base it on the 255. You're going to base it on the 255, the 84,915 joules. You would round that to 84,900 joules, and that would be positive joules. It would be positive joules because of the endothermic being melting. You need the heat to melt for both these examples. And so you have positive joules, positive delta H of fusion, okay, delta H of fusion, and you would have those numbers all be positive and your joules be positive for these two answers. So going through these two problems, you guys should be able to go through the homework, at least get a good start on it. And as you go through the homework, it's going to be on the pages that we have for your homework, which is right on this slide here. You guys have this copy, and I want to make sure you can read the numbers. I can view it a little bit bigger for you here. Okay, let me go a little bit better here on the view. Okay, we have 25.7 grams. This is of methanol at its melting point. You got to calculate the heat. So you're going to use methanol melting with 25.7 grams. The next question is going to be how much heat evolves when 275 grams of ammonia condenses. So again, you have to look on the list of constants. And so you're going to do methanol boiling, I believe it was, methanol boiling. Let's check again, methanol boiling, I believe it was. Yeah, methanol melting. So you're going to use methanol that's melting, and you're going to use the 101. You're going to use the 101. Let me use the right thing here. Why is it not working? We're going to use the methanol melting here for the first question, and then we're going to use the Um, Bear with me here, guys. The next question, we're going to use ammonia condensing, and then I changed 25, if you follow with me here, guys. Wet mass of ethanol freezing, and you're going to have to change the kilojoules to this large number of joules. So we're going to use this. So basically, you're going back to your list here, your list of values that you have on the reference list here, and find those values here. Okay, from what was asked on the question. So again, let's go back here. Um, you're going to use ammonia condensing and ethanol freezing. Ethanol is going to be freezing. So you're going to use this one for ethanol freezing and ammonia condensing, which is going to be this value here. And notice this one's negative, this one's positive, this one's negative, so you have to follow up with that, and those energies should be negative as well. Okay? Now, just to help out, I have the answers too for the homework. So let me just give you those right now while we're going through this again. And I just want to point out that the question 25 has changed just because it talks about combustion. So you should get this answer for 23, and then this answer, I believe, for 24, and thought we had an answer for for 25. I believe that's the answer for 25. So hopefully these all can help you this weekend, and then we'll talk about any questions you have on Monday. Also, when you go through these questions, they're going to ask you also, when you look at the solid here to the liquid, is it absorbing energy or releasing energy? Solid to liquid is going to be melting. From gas to liquid, you're going to be condensing. From liquid to gas, you're going to be boiling, and so forth. Tell me, is it positive or negative? That's all you're answering on number 79. The next question is on water. You're freezing it. So again, go to the list and look up water freezing, multiply it by the 11.8 to get the heat released. It's not too bad of a math to do. And then these questions, you're telling me up above the arrows, what's going on here? What is the phase change going on? And generally, when you go this direction, is energy being released or given off? Released and given off, or is it absorbed? When you go this direction, is the energy released or given off? Just tell me about those by those arrows. Now, everything below the red line, there's no need to do any of that work right now. I got a lot more to show you about that next week. Okay, so I will record a little bit more about the graph questions too here, and you'll be getting that as well. Bye-bye.